This is Unit 10, Lesson 8, Exponential Growth and Decay Word Problems. Remember earlier in the chapter, we used the equation y equals ab to the x. And that was our exponential growth and decay equation. The a was the initial amount. Your b was either greater than 1 or between 0 and 1, and it determined whether it was exponential growth or decay. Your x was the amount of time, or it could be in days or weeks or months, whatever it is, years even. And then the y was the final amount after a certain amount of time had passed. In exponential growth and decay word problems, we're now going to work or use this formula. And this formula is y equals ne to the kt. It works very similar to the y equals ab to the x formula, but there are a couple small differences. Your y is still going to be the final amount after a specific time. Your n is now going to be your initial amount. So like if it says we start with 100 bacteria in a dish, then 100 would be your n, your initial amount. So that hasn't changed. The only thing there is it's just a different variable. Your e, that is an exponential equation using e. Instead of having to find that b value, e is going to be there. And then k is going to be a constant, and that constant will be specific to the situation or the problem. Once you find k, your k value will be the same for every single problem you're doing with that specific situation. So like if you're talking about a bacteria changing over time in a petri dish, then that k value that you get for that problem will be the same k value throughout that entire situation, whether it lasts for years or weeks or months, whatever it is. And then the t value is the amount of time. In this section, this y equals ne to the kt formula, we're going to use this to find half-life problems or to solve half-life problems, which are problems that show up quite a bit, not just in math, but in science. And it's important to understand how to use exponential growth and decay problems to figure out different situations. So in the first problem, it says, a biologist is researching a newly discovered species of bacteria. At t equals 0 hours, he puts 100 bacteria into what he has determined to be a favorable growth medium. 6 hours later, he measured 450 bacteria. Assuming exponential growth, what is the growth constant k for the bacteria? Round k to 2 decimal places. How many bacteria are there after 10 hours? Okay, so our initial time at t equals 0, he put 100 bacteria into the dish. So that would be our n value. So for this problem, n is 100. It says 6 hours later, he measured 450 bacteria. That's an ordered pair, 6, 450. Now, your 6 is your unit of time. Your 450 would be the amount after 6 hours. Assuming exponential growth, what is the growth constant k for the bacteria? So if this is our formula, y equals ne to the kt, we know that n is 100. That's what we started with. E is our exponential. We don't know k, but we do know that after 6 hours, we now have 450 bacteria in the dish. So we can solve this equation using natural logs to get an answer. So if I divide 450 by 100, that gives me 9 over 2, and that equals e to the 6k. I can put a natural log in front, so I've got the natural log of 9/2 equals the natural log of e to the 6k. And if I do that, this natural log and the e cancel each other out, leaving me with 6k over here. And I've got natural log of 9/2 still on this side. Now all I have to do is divide both sides by 6 to figure out my k value. That I can put into Desmos. So I'm going to go over to Desmos and do natural log of 9/2 divided by 6. So natural log of 9/2, I'm going to put that in parentheses. Now 9/2 is 4.5. I think it'll be a little bit easier to put it in as 4.5, and then that's over 6. We were dividing by 6. And you can see there that gives us 0.4 0.25067, and I believe they told us to round that to 2 decimal places. Yes, it says round K to 2 decimal places. So if I do that, K is equal to 0.25. And so that will be our K value for this entire problem. So we know now that K is 0.25. So I can plug that into my equation. So now my new equation is y equals NE to the 0.25 T. And then I can find what they're asking me to find. It says, how many bacteria are there after 100 hours? My N was 100, my initial number of bacteria. So if I've got that, they're wanting to know how many bacteria are in there after 10 hours. So I'm going to replace T with 10. So I have y equals 100 E to the 0.25 times 10. And at this point, I can put all of that into Desmos at the same time. So that would be 100 times E, and then that is to the 0.25 times 10. And if I look here, I can see my answer. And we'll round to the nearest bacteria. So that's 1,218 bacteria. So our Y is 1,218 bacteria. Another example, Y equals Ne to the KT, and they tell us that the radioactive gas radon has a half-life of 3.8 days. Okay, this term half-life is very important when you're talking about science. A half-life tells you how much time it takes for an amount of a particle to decrease to half its size. So they're telling you that the half-life of radon is 3.8 days. So if you think about it, if you start with 1 ounce of radon, it takes 3.8 days for it to decrease to 1/2 ounce of radon. If you have 100 ounces, it takes 3.8 days for it to decrease to 50 ounces, and so forth. So it says how much of a 5-gram sample remains after 4.2 days. Well, we have to first figure out what the K value is for this situation. So what I'm going to do, I'm going to write my formula, and I'm going to suppose that I start with N equals 100. Now, you're going to have to figure out how much you want to start with. We don't use the 5 grams. That 5 grams is not our N at first. It will be in a few minutes, but we first have to figure out K. So the first thing we have to do is pick some random amount for your initial starting amount. And I always like to use an even number, because if it's a half-life, we're going to say that Y, if we start with 100, will be 50. And we know that it takes 3.8 days to get down to that 50. So our initial amount, we just made a random value of 100. E to the K, we know that it takes 3.8 days to get the half-life. So we're going to put 3.8 in for T. And then half of our initial starting amount was, or is, 50. So that's what goes in for my Y. The purpose of doing this is to figure out what our K value is, because remember, our K value is going to be consistent throughout this entire situation. So if I divide 50 by 100, I get 0.5 equals E to the 3.8 K. I'm going to put a natural log in front to get rid of the E. So natural log of 0.5 equals 3.8 K. Remember, if I put natural log in front of the E cancels. Then I would divide by 3.8 on both sides, and I can go to Desmos to figure out what K is. So I'm going to put natural log of 0.5 divided by 3.8 into Desmos. Natural log of 0.5 divided by 3.8. When I do that, I get a K value of negative 0.182. Now I'm going to round that to 3 decimal places. Usually when I'm doing half-life, I get my K value to 3 decimal places. So that was a negative 0.182. So that leaves me with my new equation, Y equals NE to the negative 0.182. So if I plug in, using the information they gave me, how much of a 5-gram sample, that's my N in this situation, remains after 4.2 days. So we're trying to find y. When we start with 5 grams, our K value is the negative 0.182, and we're multiplying by the 4.2. And again, once you find your K value, everything else is done in Desmos. There's not a whole lot of work to these. It might be a good idea to have a piece of paper to write this stuff down on so that you make sure you're plugging it into Desmos, going back and forth between the different screens. So if I go into Desmos, I'm typing in 5e to the negative 0.182 times 4.2. And the negative 0.182 times 4.2 is all an exponent. And so that gives me 2.328. So y equals 2.328. And if you think about that, 2.328 is less than half of the 5 grams we started with. It takes 3.8 days to get to half of this amount. So it would take 3.8 days to get to 2.5 grams. So it would make sense that this would be a little bit less than half going the 4.2 days. So you can kind of guesstimate whether that is a reasonable answer or not based on the information that they gave you. A certain type of bacteria doubles in population every 6.5 hours. So this one's opposite what we just did. This is telling you about the population doubling every 6.5 hours. So whatever we start with will double in 6.5 hours. So this is the opposite of half-life problems. Given that there were 100 bacteria to start with, how many bacteria will there be in 36 hours? All right, so we're going to use the formula y equals NE to the KT. Now, usually when a student sees this problem, here's what they would do. They would take this information, they know it doubles in population every 6.5 hours, and given that there were 100 bacteria to start with, how many bacteria will there be in 36 hours? They will try to plug in, and they'll do, okay, y equals, we're starting with 100, e to the k, we don't know what that is, and times t is 6.5. Now, there's nothing wrong with plugging in like that, but the problem is you haven't figured out what k is, so there's no way to solve this problem because you've got too many variables. That's why we need to recognize what this is telling us. It's telling us that your population doubles in 6.5 hours. We have to deal with that first to find our k value so that then we can plug into this equation. So that's what I'm going to do next. I'm going to find k first. So if I do that, I'll go ahead and use the 100. I'll say, okay, it starts with 100. So if I've got y equals NE to the KT, N is 100. Now they're telling me it doubles every 6.5 hours. So 100 will become 200, and that takes 6.5 hours to happen. The E is the exponential. I don't know what K is, but I know that T is 6.5. So if I do this and I divide by 100, 2 equals E to the 6.5K. To get rid of the E, I put a natural log in front. So I've got natural log of 2 equals 6.5K, and I can divide by 6.5. So K is equal to natural log of 2 over 6.5. I go to Desmos, and I put in natural log of 2 divided by 6.5. That gives me 0.1066. I'm going to round, so that would be 0.107. So my K value here will be 0.107. And if they don't tell you how much to round by or what decimal to round it to, always do 3 decimal places. So K is 0.107. I can put that in for K here. So if I do that, I've got Y equals 100 times E. K is now 0.107. And then be careful here. This 6.5 was for the double life, or doubling the amount. They want to know how many bacteria there will be in 36 hours. So see, if you don't replace that 6.5 with the 36, you'll get that wrong because you're not accounting for what they've asked for. So I'm going to put this into Desmos. 100 E to the 0.107 times 36. 100 E to the 0.107 times 36. And that gives me 4,709 if I round to the nearest whole number. Here's another half-life problem. The half-life of a blue radioactive substance located somewhere deep inside a lake is 7 weeks. How long would it take for 900 pounds of it to be reduced to only 10 pounds? Okay, so first I have to find K. Anytime you have a half-life problem, your first thing to do is find K. We use Y equals NE to the KT. And it says the half-life takes 7 weeks. So I'm going to start with an even number. The simplest even number to start with would be 2. So I'm going to let n equal 2. I know it takes 7 weeks for that 2 to decrease to 1, half of it. That equals e to the k times 7. So 1/2 equals e to the 7k. Finding your half-life is going to be the same work every single time. I'm going to put a natural log in front. That's natural log of 0.5. Equals 7k. I get k by itself. So natural log of 0.5 divided by 7. If I put that into Desmos, natural log of 0.5 divided by 7. That gives me a negative 0.099 as my k value. So I'm going to go back. Negative 0.099 is my k value. So k is equal to negative 0.099. That's my k value for the entire problem. So I'm going to use the same formula, y equals NE to the KT, and now I know that k is negative 0.099 times t. So go ahead, pause the video, see if you can finish this problem using this question. How long would it take for 900 pounds of it to be reduced to only 10 pounds? Go ahead and see if you can plug in and get that answer. So this one's a little bit different. If we plug in, they're asking us how long it takes 900 pounds to be reduced to 10 pounds. They want to know how long it takes for y to get to 10, so they're asking us to find the time. So if I do this, 10 divided by 900 is 1 over 90. So natural log of 1 over 90 equals negative 0.099t. If I divide by that negative 0.099 and then I go into Desmos and put that in, I end up getting 45.45. My t value is 45.45. And so since this was a full number of weeks, I'm just going to say, I'm going to just keep it rounded to 2 decimal places here. Usually in Delta Math or whatever worksheet you're doing or whatever, they're going to tell you what to round to. So this would be certainly fine, 45.45, and that is the number of weeks. So it takes 45.45 weeks to go from 900 pounds to 10 pounds. The half-life of a certain Venetian substance is 90 days. How long would it take for 80 pounds of it to be reduced to 20 pounds? All right, go ahead and pause the video, see if you can get this one done on your own, and then we'll go over it in a few minutes. So looking at this one, the first thing I did was find the half-life. So I let y equal NE to the KT. I let my initial amount be 2, and then I know the half-life would decrease that down to half its original amount, 1. And they told me the half-life was 90, so I put 90 in for t. So 0.5 is equal to e to the 90k. I put a natural log in front. Natural log of 0.5 equals 90k. Divide by 90. I put that in Desmos to get k equals negative 0.008. I just rounded to 3 decimal places. Then I plugged that into the k because our k is consistent throughout the entire problem. So y equals NE to the negative 0.008t. Then it asks how long. So they're asking us to find a time. How long does it take for 80 pounds to reduce to 20 pounds? So we start with 80. We want to know how long it takes it to reduce the final amount to 20. So if I put that in and divide by the 80, I get 0.25. That equals e to the negative 0.008t. I put a natural log in front to solve the exponential equation, and then divide by the negative 0.008 put that into Desmos, and I ended up with t equals 173.3 days. Here's another one. The half-life of a certain bizarre glow-in substance is 50 weeks. How long would it take for 400 pounds of it to be reduced to 90 pounds? So go ahead, see if you can do this one on your own, and we'll go over it in just a minute. So for this one, first I found the half-life. I use y equals ne to the kt. I let my initial amount be 2. Half of that would be 1. We know it takes 50 years for it to decrease to half its size. So if I divide by 1 divided by 2 is 0.5. Natural log of 0.5 equals 50k. I divide by the 50 to give me a k value of negative 0.014. I plug that in for my k value for the rest of the problem. They're asking me how long it would take for 400 pounds to be reduced to 90 pounds. 400e to the negative 0.014t equals 90. I divide 90 by 400 and get 9 over 40 equals e to the negative 0.014t. To get rid of the e, I put a natural log in front of both sides. So I've got natural log of 9/40ths and then divided by the negative 0.014. I put that into Desmos, and I end up getting a 106.546. So that means my answer is a 106.55 weeks. So my answer is a t equals 106.55 weeks. The next section will be dealing with other types of exponential and logarithmic equations, dealing with some real life data as well.